Okay, hello and welcome everybody. This is the worked examples for integration by parts, Fourier and Taylor series section. And we'll just be looking at a lot of examples of computing both of these objects. And maybe I'll show you a few of the plots of them as well, so you can get an idea of how these series converge. So with that said, let's just jump right in. We're just going to work through a lot of examples, like I said. Let's find the first four terms of the Taylor series for x cosine x centered at x not equals 0. And I think this is something to keep in mind. Every time you're going to be asked for a Taylor series, you're also going to be provided with a center. So all Taylor series are given a center. So this x not equals 0 will always be given to you. That makes your life pretty easy. You know right away how you're going to try to construct these objects. And it's good for me to write this down again, just so none of you forget. When we're constructing these, they always look like this. But in particular, if x naught is 0, then we're actually computing the following. F, the nth derivative evaluated at 0, since where that 0 comes into play. And it also comes into play up here. So both of those get replaced by 0. And even better than that here, when I just say the first four terms, we're going to go ahead and construct just the first 4, which would be f with 0 derivatives on it. And then we'll have x minus 0 to the 0 power, which is just x to the 0 power over 0 factorial, plus the first derivative at 0, x to the first power over 1 factorial, plus the second derivative at 0, x squared over 2 factorial, and then the third derivative at 0, x cubed over 3 factorial, because that's a total of 4 terms. So in reality, we're going to be calculating those objects. And to do so, the most important part in all of these is really being able to evaluate all of these effectively. So we're really going to spend all of our time evaluating these coefficients, which will just be the first 4 derivatives. Really the first 3 derivatives as well as the 0th derivative. So with that said, let's go ahead and say, okay, if f of x is x cosine of x, then we can take the 0th derivative, and simply itself. We can take the first derivative using the product rule, because I see a product there. So I'll take a derivative of x, that's going to give me a 1, times cosine x. Then I'm going to add x and take a derivative of cosine x, which is negative sine x. If I want to take a second derivative, I'm just going to take a first derivative of what I just saw above. So taking a first derivative of this. Maybe it's to my advantage to write this out a little bit more clearly. That's negative x sine x plus cosine x. I'm just going to take one more derivative from the above, and we've got another product rule going on the first term. So there's a negative x, that's going to give me negative 1. Sine comes along for the ride. I'm going to add negative x. I'm going to take a derivative of sine, which gives me cosine x. Finally, a derivative of cosine x is negative sine x. And I could go ahead and simplify this, combine like terms. Looks like I have 2 copies of a negative sine x sitting around, as well as negative x cosine x. And then if I want to calculate my third derivative of f, I'm calculating a derivative of that term. I will have one more round of a product rule. The derivative of negative x is negative 1. I'll be multiplying by cosine of x, and then adding derivative of cosine x, which is negative sine, but there is also a negative in front of the x there, so those will both cancel, and I'll be left with x sine x, and then minus 2 times the derivative of sine here, which is cosine of x. Now you may think that that's enough for me to gain these 4 coefficients that I care about, but it's not quite. When we're dealing with a Taylor series, and I have all of these computed, now we must evaluate these at the center, which in this case, the center is x not equals 0. So the fact that there's a 0 there, a 0 there, a 0 there, and a 0 there, I actually have to go ahead and evaluate each of these. Let's not forget some of our favorite values for cosine and sine. In this case, we have our unit circle, but we're evaluating all of them at 0. So 0 rotations around the unit circle. The x value there is 1, the y value is 0. So cosine of 0 is 1, and sine of 0 is 0. It's going to be very helpful to us as we evaluate. So let's go ahead and evaluate. 0 derivatives at 0. I'm plugging a 0 in there. That's 0 times cosine of 0. Or 0 times 1, which is still 0. A first derivative evaluated at 0. I'm looking here. It's going to give me negative 0 times sine 0 plus cosine 0, which is negative 0 times 0 plus 1, which is 1. Two derivatives on f evaluated at 0. I'm looking here. I'm going to get negative 0 times cosine of 0 minus 2 sine of 0. And what am I left with? I'm left with negative 0 times 1 minus 2 times 0, and I have a 0 here. My last term, I'm going to be evaluating the third derivative here at 0, and that's going to give me f of 3 derivatives at 0 gives me negative 1 times cosine of 0 plus 0 times the sine of 0 minus 2 times the cosine of 0, and I'm left with negative 1 times 1 plus 0 times 0 minus 2 times 1. I end up with negative 3. So what I've calculated here is 4 coefficients, because I'm looking for the first 4 terms of the Taylor series. And in my Taylor series, those coefficients, here, 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 and here, are all attached to these monomial terms. So I'll go ahead and add those 4 monomial terms to my 4 coefficients here. I just have a 0 times x to the 0 over 0 factorial plus 1 times x to the first power over 1 factorial plus 0 times x squared over 2 factorial plus negative 3 times x cubed over 3 factorial. So obviously my terms that have zeros in front of them can be omitted, and 1 factorial is equal to 1, 3 factorial is equal to 6. You'll all get used to 3 and 4 factorial soon enough. So what I have going on here is 1 times x to the first power, also known as x, plus negative 3 divided by 6, also known as minus 1/2 x cubed. So this is actually the first 4 terms, even though 2 of them were 0, of the Taylor series. And this will be approximately x cosine x. That's kind of what the Taylor series gives us the ability to do, is approximate. We approximate x cosine x with a cubic polynomial. Now, what do I mean by approximating with a cubic polynomial? Well, I'll go ahead and provide a plot here. So here we have a plot, and in the red, sorry, in the cyan in this video, so the line here is obviously a cubic polynomial, and then the other line is x cosine x. So we have here is x cosine x against the cubic polynomial, which is x minus 1/2 x cubed. And if we zoom in and just look at the way these functions behave near the center, which is at 0, so if we look near this point, which is the center, the functions are basically the same. They have the exact same properties. We would find out if we added more and more terms to the Taylor series, we would get closer and closer to this x cosine x that we're looking for. So that's what it means to approximate with a Taylor series. You get a cubic that looks a lot like the original function, at least near the point. And so with that said, let's go ahead and try the same problem, except let's modify the center. So let's move the center to maybe this point right here. This point, by the way, is pi over 2. So let's go ahead and modify the center to pi over 2. This is an exercise. Find the first 4 terms in the Taylor series for x cosine x centered at x naught equals pi over 2. Well, we can get away with everything we did before. The only thing that's going to change is that rather than evaluating my 4 derivatives at 0, I'm now going to evaluate those 4 derivatives at pi over 2. So I've gone ahead and copy-pasted those 4 derivatives from the earlier problem, but now we need to evaluate at the new center, which is pi over 2. That's not going to be too much work. Let's go ahead and do it. Pi over 2, keep in mind on our unit circle, is going to be the point at the top here. So at the top we have at 0, 1, the next value is 0, so cosine of pi over 2 is 0, sine of pi over 2 is 1, This is going to modify all sorts of things in our results here. So let's go ahead and look. We've got x times cosine x. So that's going to be pi over 2 times cosine of pi over 2, which is going to give me pi over 2 times 0, which is going to be 0. And then we have f evaluated at 1, or f of the first derivative of f evaluated at pi over 2, which is going to be up here at pi over 2. That's negative pi over 2 sine pi over 2 plus cosine pi over 2, which is going to give me negative pi over 2 times 1 plus 0, which is negative pi over 2. The second derivative of f at pi over 2 will be this term. Value at pi over 2, that's going to be negative pi over 2 cosine pi over 2 minus 2 sine pi over 2. And I'll end up with negative pi over 2 times 0 minus 2 times 1. I end up with negative 2. And finally, the third derivative of f, evaluated at pi over 2, will give me this one at pi over 2, so negative 1 cosine pi over 2 plus pi over 2 sine pi over 2 minus 2 cosine pi over 2 is going to be negative 1 times 0 plus pi over 2 times 1 minus 2 times 0 is going to give me pi over 2. So these are now my 4 Taylor coefficients. And we'll keep in mind that the Taylor series depends intimately on the center in 2 places, right? So we have f of n at the center, but we also have this notion of x minus the center to the nth power over n factorial. And so if I write out my first 4 terms, this is going to be x minus pi over 2 to the 0 power over 0 factorial, and the 0th derivative at pi over 2, plus the first derivative at pi over 2, x minus pi over 2 to the first power over 1 factorial, plus the second derivative at pi over 2, x minus pi over 2 squared divided by 2 factorial, and the third derivative at pi over 2, x minus pi over 2 cube over 3 factorial, and so on. But those are my first 4 terms, and I've just calculated 1, 2, 3, 4 coefficients. If I go ahead and plug those coefficients in and write out my 4th order polynomial, I have that x cosine x is approximately equal to what I've just calculated. That was a 0 times, this one was a 0, times x minus pi over 2 to the 0th power over 0 factorial, plus negative pi over 2 times x minus pi over 2 to the first power over 1 factorial, plus negative 2 times x minus pi over 2 squared over 2 factorial, plus pi over 2 x minus pi over 2 cube over 3 factorial. And if I simplify all of this, the 0 can go away. My 1 factorial is just 1, 2 factorial is 2, 3 factorial is 6. I end up with negative pi over 2, x minus pi over 2, minus, now there's a 2 divided by 2, so those cancel, x minus pi over 2 squared, plus I have pi over 2 divided by 6, I have pi over 12, x minus pi over 2 cubed. So this now is my polynomial, my first 4 terms of the Taylor series. And you'll notice it's been modified quite a bit, but that's because I've modified my center. If I go ahead and find a plot of this polynomial, we can see the Taylor series provided at the bottom, or the approximation. And now we don't have good, we lose good approximation at the earlier center that we had before, but all of a sudden we gain good approximation at pi over 2. And so this is really how the Taylor series behaves. It finds things locally at a point. You can see just how well we approximate around that point. So you can gain these polynomials that locally approximate functions. Let's go ahead and move on to a Fourier series problem. Okay, so let's find the Fourier series. For the function x squared minus 2x plus 1. And recalling the formula for the Fourier series, we have the following. A function is equal to an infinite sum, and the coefficients are determined by the integral from negative pi to pi of f of x e to the minus I n x dx, e to the I n x. And in this case, our function f is right here, so we'll be replacing that f of x with an x squared minus 2x plus 1. Now in general, nobody likes computing Fourier series as much as computing Taylor series because integration is always a more difficult process than taking derivatives. But we can go ahead and do our best and try to find this antiderivative here. We're going to put x squared minus 2x plus 1 into the integral e to the minus I n x dx. And what's going to happen is I can distribute my e to the I n x to all three terms. And actually, because it's integration, I can distribute the integral to each of the three terms as well. And what I end up with is three integrals. The first one is minus pi to pi of x squared e to the minus I n x dx. The second one is minus 2 times the integral minus pi to pi x e to the negative I n x dx. And the third case is plus the integral minus pi to pi of 1 times e to the minus I n x dx. This makes my life a little bit easy because it's time to be clever and recall that in the last video we evaluated this. As I times negative 1 to the n divided by n. So that makes our life easy on exactly one of these three terms, but unfortunately the other two we are going to go ahead and go through the work for. This one's not too bad, the very final one, because there's no coefficients on the e. I can just take an antiderivative of e to the I n x, and that gives me 1 divided by negative I n, e to the negative I n x, evaluated at minus pi and pi. In other words, this is e to the minus I n pi minus e to the minus I n negative pi. I can cancel that, put a pi here, and divide it by negative I n. And if I want to calculate these specific values, let's recall that I do that with Euler's formula. Or even I'm going to give you one extra shortcut today. And the shortcut is just going to be that e to the I pi is negative 1. Euler's formula always tells me that. Which means, by exponent rules, I can write this as e to the minus I pi to the nth power minus e to the minus I pi to the negative nth power, all divided by negative I n. This is going to be negative 1 to the n minus negative 1 to the negative n, all over negative I n. And negative 1 to a negative power is the same thing as negative 1 to a positive power. So I have two copies of negative 1 to the n that I'm subtracting from each other. They cancel, and I get 0 over negative I n. Now I do want to pull off a really big caveat here. You may want to say that this is equal to 0, but that's not true when n equals 0. Because if I go back to the beginning, in this sum, n equals 0 is a very real possibility, so I do need to consider that case separately. But for all other cases, this will in fact be equal to 0. So that gives me an evaluation for that final term, and thus we're just left with evaluating this integral. So this integral, we're going to have to go through a little bit of integration by parts for, because I have an x squared against e to the I n x dx. In integration by parts, I always want to choose this as g prime, which means I'm going to choose this as f, and that's going to give me f times g, the antiderivative of that complex exponential, evaluated at the bounds. Then I'm going to subtract f prime, so a derivative of x squared is 2x. The antiderivative of g prime, 1 divided by negative I n, e to the negative I n x dx. And unfortunately, I have one more round of integration by parts here, g prime x. That's due to the fact that I started with an x squared. It's going to be 2 rounds of integration by parts. Time to go through the work here. Just on this term, integration by parts on that term, I'm going to have f times the antiderivative of g will now give me 2 copies of minus I n in the denominator, e to the minus I n x, evaluated on my bounds of minus pi to pi. Then I'm going to subtract, but there's already a minus sign here, so I'm going to add an integral of a derivative of f, which the derivative of 2x is just 2, and I still have my other coefficients sitting around, e to the minus I n x dx from minus pi to pi. And so this term I will finally have to integrate one more time. That's going to give me 2 over I n cubed, e to the minus I n x evaluated on my bounds. So I need to go ahead and evaluate this term on the bounds. this term on the bounds, and this term on the bounds. So let's do that. Plugging everything in, putting pi in for both copies of x and minus pi in for both copies of x. I'm left with pi squared divided by negative I n e to the negative I n pi minus negative pi squared over negative I n e to the positive I n pi, because the two negative signs cancel. It's my first term. My second term will be minus 2 times, I'm evaluating pi there, and negative pi there, and there. Negative 2 times pi divided by negative I n squared, e to the negative I n pi. Then I'm going to subtract the lower bound, but there was already a minus sign there, so I'm adding the lower bound, 2 times negative pi divided by negative I n squared, e to the positive I n pi. And then my final term here, plus 2 over I n cubed, e to the minus I n pi, minus 2 over I n cubed, e to the positive I n pi. When I go ahead and simplify all of these exponentials, recall they're all going to be negative 1 to the nth power for the same reason I described above all the way up here. They're all going to be negative 1 to the nth power. I'm going to have pi squared over negative I n, negative 1 to the n, minus pi squared over negative I n, negative 1 to the n. I'll have minus 2 pi divided by negative I n squared, negative 1 to the n, plus negative 2 pi divided by negative I n squared, negative 1 to the n, plus 2 over I n cubed, negative 1 to the n, minus 2 over I n cubed, negative 1 to the n. Now it's really important to notice here, there's a positive term minus itself. Here's a positive term minus itself. The only terms that survive are here in the middle, and they survive with a minus sign and a minus sign. Let's look in the denominator. I have a negative I squared in both denominators. Negative I squared is a positive I squared is negative 1. So all of the negative signs cancel, and I end up with 4 pi negative 1 to the n divided by n squared. So I went through all of that work just to end up with 4 pi negative 1 to the n over n squared. Now keep in mind, that was just this term here, 4 pi negative 1 to the n over n squared. I've already evaluated this term, and down and to the right, 0 over negative I n, also known as 0, is this term. 0 when n is not equal to 0. Okay, so what have we learned then? We've learned that the Fourier series is equal to the sum n going from minus infinity to plus infinity, but n not equal to 0 of the cases we've seen above. So this is 4 pi times negative 1 to the n divided by n squared, plus the case here, which was I times negative 1 to the n over n times negative 2 times negative 2. And in fact, this term needs the 1 over 2 pi on it, coming from that. However, this one from our previous video already included the 1 over 2 pi in it. And then the final term is equal to 0 so long as n is not equal to 0. Therefore, we have this times e to the I n x, and then we do need to add the term when n is equal to 0. And what should that term look like? Well, let's scroll up. Let's scroll up to here and notice that in the case when n is 0, these exponentials are both equal to 1. And so the n equals 0 case is actually fairly straightforward to compute. It's simply going to be the situation of 1 over 2 pi times the integral from minus pi to pi of x squared minus 2x plus 1. Both of the exponentials have disappeared when n is 0. So let's go ahead and calculate that. This integral, thankfully, is much easier than the other ones we've had. We have 1 over 2 pi times the power rule, which will be x cubed over 3, minus x squared plus x, evaluated at the bounds minus pi to pi, and we end up with pi cubed over 3 over 2 pi, minus pi squared over 2 pi, plus pi over 2 pi, and then we subtract evaluating at the lower bound, which will be negative pi cubed over 2 pi, pi cubed over 3, and then minus negative pi squared over 2 pi, and finally plus negative pi over 2 pi. If I go ahead and simplify everything here, what I have is pi cube over 3 minus negative pi cube over 3. So that's actually going to be 2 copies of pi cube over 3, twice pi cube over 3 times 2 pi. I'm going to have a negative pi squared and a minus a negative pi squared. These terms actually end up canceling. And finally, I have a pi over 2 pi minus negative pi over 2 pi, also known as plus pi over 2 pi. I have plus 2 pi over 2 pi. And this will all together give me, once I cancel the 2's and 1 copy of the pi's there, as well as both of these, I end up with pi squared over 3 plus 1. So that means that this entire term, when n equals 0, can just be replaced with my result, pi squared over 3 plus 1. This is the Fourier series for my function x squared minus 2x plus 1. Let's actually see this in action. I realize this is a whole lot of computation and something that I think probably none of you actually want to do, but let's just see the approximations. So if I did my function x squared minus 2x plus 1, and maybe I'll say it's approximately to the case where maybe I'll go from negative 5 to positive 5 terms, and then, what we just calculated, e to the I n x, I get the following plot, where what you're looking at in the cyan here is the Fourier approximation, and the gray is my function x squared minus 2x plus 1. And so Fourier has this very interesting behavior of oscillating around the function we're trying to approximate. It's oscillating there around the function we're trying to approximate. Let's go one step more and run, instead of only up to 5 terms, let's run this up to 50 terms. When I run it up to 50 terms, I end up with the approximation shown here, and here you can see now in the cyan is the Fourier approximation, and in the gray is x squared minus 2x plus 1. And so you can see these oscillations are getting so infinitely small around where I'm actually trying to approximate the function until I get to this endpoint. Now what is that endpoint? If I draw a vertical line here, you can see that runs in at x equals pi, and it comes back here at x equals negative pi. And so this is why we're working on this interval, negative pi to pi. You see some bad behavior at the endpoints, but right in the middle, everything behaves really, really well. Okay, and I know this has been a long day, a lot of hard mathematics that's happened, especially with these integrations and integration by parts. I want to make you feel better. I want to assuage maybe your fears about this. I will not make you perform any of these integrals for the Fourier series. I realize they're really, really tricky, but I did want to see you'd all see why the integration by parts is important and how somebody would actually go about these calculations for the Fourier series. But for this course, we won't go through needing to know the calculations of the Fourier series for any sorts of quizzes or exams. You will have to take derivatives to use the Taylor series, though. So go ahead and just take from that what you will. It's really good to see how the Fourier series is actually constructed, even if maybe I'm not going to make you go through the calculations. Anyway, I'll see you in the next video. Bye.